I'm Mark Ruta. I worked with the Draper Laboratory with Izzy, Marianne, Nicole Rishin, and two of them are over here. Say hi, guys. And I work with also my advisors, Peyton, Joseph, and Corinne on the translation of a novel microstructured tissue fastener into a coronary stent. So what does all this mean? So basically we worked on a technology called Mantis. Mantis stands for mechanical adhesion tissue, and it's exactly how it sounds like. It's the mechanical adhesion of microstructures, and it functions like Velcro, where these microstructures are pushed into tissue, where the microstructures are like the hooks, and the loops are like the tissue. These actually are really, really small, 125 microns. If you looked at it with the human eye, like 100 of them lined up, it would literally look like peach fuzz. It's really, really small and super hard to visualize and conceptualize. And a good understanding of the first use of it was in the pediatric heart valve they first created. And this was used to help kids with heart valve problems, and they would implant this, and this implant would actually grow with the child. But the problem with this was that those blue sutures there required a lot of time to be implanted to implant the structure around the outside of the heart valve to then be implanted. So instead, they actually created this technology to replace those sutures on the outside, the blue ones there, with this technology to adhere the outside structure to the soft tissue. So they created this technology, this adhesion technology, and they said, okay, guys, find a new device. How are we going to be able to use this now? So we looked at a bunch of different cases, and we decided to go with a coronary stent. And our reasoning for choosing a coronary stent is the market cap is $8.8 billion as of 2023, and is seen to grow in the next 3.8% in the next 7 years. And the three drivers of this reasoning is 1, obesity growing in the United States. 2 out of 3 people in the United States have obesity, are shown to be overweight. 2 is just different cardiovascular diseases. As of 2016, 48% of people have a cardiovascular disease, and also technological growth in the area. We can see bare metal stents, which was the first one I showed you guys, which is just a mechanical structure that is inserted into the coronary artery. There's also other technological advancements like a drug-eluting stent, which is a stent that is covered in immunosuppressant that also reduces tissue growth. So these coronary stents, though, have a bunch of different problems. And the two we focused on is stent recoil and in-stent restenosis. But first, how is a coronary stent implanted? So it's implanted with a balloon catheter through a vein. It's put up to the heart, or shown here on the picture on your guys' right, and it's actually inflated, the balloon is inflated, and then the stent is locked into place. However, there's 2 problems that happen. One is stent recoil is once this stent is implanted into the artery, it actually bounces back in on itself, mechanically failing, so the size of the blood vessel actually gets smaller. This is a problem because blood flow can't happen in the artery, which then causes like blood clotting and like further complications of the heart. The other one is in-stent restenosis. The same thing is when the thing is expanded and put into the artery, the cells around on the walls actually grow over top the stent, also reducing the size of the blood vessel. And this is a problem as well because then we have poor blood flow, also more clotting occurs, and that's a problematic thing for stents. So our team decided to hypothesize that we can actually use this Mantis technology by adhering these microstructures on the outside of this coronary stent by allowing to reduce stent recoil by mechanically adhering the stent to the outside of this wall, which mechanically holds the stent to the walls, like putting Velcro on the outside of it. And then for stent restenosis by having an immunosuppressant on top of this, which then because these microstructures on top of the stent, it actually increases the surface area technically, which will then allow us to have more drug being put in the specific spots we want. So how do we test all these different hypotheses we talked about? We're going to go to 2 different veins of thought. The first one is our mechanical testing. How do we prove that we can actually stick this really small microstructure into a coronary artery and actually have it work? So we tested all our testing on 1 microstructure for the puncture pull-out test, as seen in the infographic on the far, your guys' left. And what this did is basically have a linear motion system where we would push down this specific microstructure into the tissue. The way we got this tissue is we went to the butcher, we grabbed the heart, we took off the coronary artery, we opened it up, so we actually had the exact tissue we wanted to push this microstructure into. We pushed the microstructure into it and pulled it out. And we wanted to see if this microstructure would adhere to the tissue. And as we can see in the pictures on your guys' right, we can actually see the microstructure being pushed into the tissue and being pulled out, and it's actually holding onto the tissue. Exactly what we want to see, that mechanical adhesion. And the bottom is showing just a more outside view of it, and you can actually see the scale of how small this microstructure is. The next test we wanted to do is a tensile test, and basically the way we did this is by loading up the Mantis coupon with an array of them, around 40 of them, and we put the tissue on top of it and we pull it across of it. And this helps us test if like a blood flow situation was happening. We can actually see the different forces being pulled across the microstructures instead of on top of them. And this actually showed a great statistical significance, showing up to 0.4 newtons of strength in comparison to its blank counterpart. So next is our drug diffusion experiment. So this experiment is different than the prior one because Draper previously had already done mechanical testing a lot. So a lot of those systems that we were just using were just iterating on top of that. We had to start with the drug diffusion from step 1. So first we had to, in a figure on your left, is our first step, which we just had to prove that we can take these microstructures and just coat them with drug. And the way we did this is by taking a drug, on which our model drug was just a fluorescent dye, and a polymer, which is just delivers the drug to our specific spot we want, and then put it on for different amounts of time of dipping it. And the way we dipped it is we literally just took our structures, we put them in for a certain amount of time, and pulled them out. And then we tested it to see how much drug was actually on those coupons. And this allowed us to just characterize how these microstructures could hold this drug that we wanted to then insert into our coronary artery. The next thing is that we needed to create a tissue surrogate. Because if we wanted to test this actually, we would not be able to visually see how the drug is diffusing if we just put it into a coronary artery. You can't see the drug. It's in tissue, it would be a problem. So instead we had to create translucent gels so we can actually visually see the amount of drug diffusing through the gels. So we use alginate hydrogels to actually create this to actually visualize how the drug is diffusing through the tissue. The next thing is our final conglomeration of both these sets together. We took our dipped coupons, we pushed them into the gels, and we left them in there for 3 hours to visually see how the gel is diffusing off the mantis structures into the gels. And this actually was, through all these tests, we have a bunch of stats, but I don't want to bore you with you guys. The end of the day is we were able to characterize the specific coating we want to do. We dipped it in for 15 seconds for 2 different dips, and that's the characterization of the coating. The gels, we had a specific mixture of sodium alginate and calcium chloride, which gave us the specific gel structure we wanted that mimicked tissues to the correct amount of diffusion. And then after being able to dip those dipped coupons into those hydrogels that we created, we were actually able to visualize the drug diffusion in a correct way that we were actually hoping to see. So what does all this mean? Basically, our goal was to reduce in-stent restenosis and in-stent recoil, and we did it, or kind of. We did it at least. we did it in a way where we can actually at least hope to see that there's a lot of benefits and a lot of good leaning forward to where if people were to pick up this testing, we'd actually be able to continue it and actually look at it in a really bright manner. And if we had more time and more money and more XYZ, we'd actually love to create a physical prototype of this where we could actually test real blood flow flowing through the stent and seeing how that would react in a coronary artery. Thank you guys so much for your time, and I'm here for any questions.
Thank you so much, Mark. Any questions? I have one. So are you or the lab continuing with this project? What's next for it? Is there a plan?
So the way the company works, it's a non-for-profit, and they function through government grants. So we're actually the last project on their grant before their money runs out, and they're waiting for new proposals or more grant money to hopefully either further this or other veins of this work, like the pediatric heart valve I talked about earlier.
Awesome.
Yeah.
Thank you, Mark. This is very impressive. So since the scale is so small on these, how are you guys physically working with the materials since they're so tiny?
So we used a lot of tweezers and a lot of, I wouldn't say it was rudimentary, but a bit of it was kind of rudimentary, a lot of microscopes and just really precise hands. For the specific testing, the reason we use those machines is because it's so hard. So if we had another world for the drug testing, we would have used similar machines as well to actually be able to do that precision dipping, because I couldn't be able to tell you how far these things are going in actually.
Thank you. It's really interesting. I have a question about stent recoil.
Yeah.
Is that instant the way you were describing it?
So it happens at various phases within it. Sometimes it's instant because just the mechanical structure fails. We insert a balloon expands, and then there's locking mechanisms on some stents. So those locking mechanisms could fail. Other ways is just over time they could fail. So different instances of instant recoil. Yeah.
And then can I ask another question about the drug diffusion?
Yeah.
So are you talking about continuous drug diffusion?
So
would it be ongoing?
So the drug diffusion is dependent on how we put the drug coating on it, but the goal would be a continuous drug diffusion over 3 weeks.
Which would be enough time for it to prevent the
Exactly.
growth.
Mm-hmm.
Okay, cool. Thank you.
Other questions?
Okay, so let's say that you had infinite amounts of money and infinite amount of time. What would you see the future of this project being?
Cool. So the up and coming, the new stents we're going to talk about would be the bioabsorbable stents, but we use a different material actually, which this allow for us to eventually have the stent to like completely disappear in the artery, right? But the problem with those is that they mechanically fail, which if we had more money, more time, we would actually push really hard for Draper to look into those, because the way they fail most is mechanically, because they're bioabsorbable, the material is a little more like fragile and not as like able to hold onto the walls. So the specific microstructures we use will be actually super helpful, and hopefully those bioabsorbable stents.
Thank you so much, Mark.
Thanks, guys.